Welcome viewers to the fifth lecture for the online series of lectures for the course of Algebraic Topology 1. In the previous lecture, we obtained the result concerning the fundamental group of circle with reference to a given base point. We have seen that this fundamental group is isomorphic to the additive group of integers. In this lecture, we will prove a few important results, namely Brouwer fixed point theorem for disk, and we'll also prove fundamental theorem of algebra using topological techniques. Before we do these things, we need a definition. Let me get started with the definition of retraction. If A is a subspace of a given topological space X, a retraction of X onto the subspace A is a continuous map R from this big topological space X to the subspace A such that the restriction of R to this subspace A is just the identity map on the subspace. Okay. The identity map of the subspace A. Okay. If such a map R exists, we say that A is a retract of X. Of the topological space X. Okay. Good. Now, the first lemma of today's lecture, which states that if A is a retract of X, then the homomorphism of fundamental groups induced by inclusion of the subspace A into the big topological space X is injective. Okay, which means that we have to prove that J star, the homomorphism that gets induced from this inclusion map, is injective. Okay, let's prove it. Okay, first of all, if R from the topological space X to its subspace A, if this guy is a retraction, okay, then it's easy to see that the composite map are composed with J. Okay, so J takes A to X, and when J gets composed with R, that map is supposed to take A to itself, right? And which is nothing but the identity map, by, we put a subscript A, in order to stress the fact we are dealing with point topological spaces. I sub A, the identity map of A, comma, small a. Okay, so A is taken to be the the distinguished point in the topological space A, big A. One therefore has for the map are composed with J, which is of course a map between this point topological space to itself. The induced, so we are considering the induced homomorphism of this composite map. The induced homomorphism are composed with J star, okay, that we know from the second lecture to be equal to R star composed with J star. Okay, this guy, and we also know from the second lecture that the identity map on the given point topological space is the induced map of this map in the point topological space is just the identity homomorphism on the respective fundamental group. Okay, and this guy is the identity map of pi 1, the fundamental group of big A with reference to this distinguished point small a, which we denote by I sub A star. Okay, good. I need some space. Let me erase this front matter. Now, since R star composed with J star is equal to I sub A star, which is, this guy is the identity homomorphism on the fundamental group, right? Okay, so with this relation we immediately see that R star is a left inverse of the map J star. R star is a left inverse of the map J star. And since J star has a left inverse, it must be injective. It's an easy result to prove. For your reference, refer to exercise 5A, page 21 of the book by Mancras. So you have to solve this exercise, okay? And then you'll see that if you have a map that has got a left inverse, it has to be injective. Okay. So from this we see that J star is injective. Okay. This is what we needed to prove. QED. Okay, so that's the first result. Now the first theorem of today's lecture, theorem 1, which we call no retraction theorem. Okay. It states that there is no retraction of this unit ball B2 onto the unit circle S1. Okay, this is what we need to prove. So the proof is simple. Suppose the contrary, we proceed by contradiction. Okay, that is S1 is the retract of B2. Suppose that there is a retraction of B2 onto S1, which means that S1 is a retract of the unit ball in dimension 2. Then the homomorphism induced by the inclusion of S1 into B2 would be injective, right? Injective by lemma 1, which we proved a while ago. Okay. That is, so let me write it. J star, the induced homomorphism of this inclusion map from pi 1 S1 comma B0. So the fundamental group of the circle with reference to this distinguished point B0 to itself, no, not to itself, to the fundamental group of the unit ball with reference to the same point, right, B0, since it's an inclusion map, right? This requires to be injective, right? To be injective. Well, this is in contradiction with the fact that the fundamental group of circle with reference to this given base point, with reference to this distinguished point B0, is non-trivial, while this guy is trivial. While the fundamental group of the unit ball with reference to the same point B0 is trivial. Okay, so there cannot be an injection from here to here. Okay, so that gives us the contradiction. So that means that there is no retraction of B2 onto S1. QED. Okay, now a very important lemma that we are going to use throughout the rest of the lecture. We need to state it first and then we'll prove it. Lemma 2, let H, the map H from the unit circle to a given topological space X be a continuous map. Okay, the following statements are equivalent. TFAE. 1. H is null homotopic. The second statement says that H extends to a continuous map. K from the unit ball to the given topological space X. And the third statement says that H star, the induced homomorphism of this continuous map H, is the trivial homomorphism of fundamental groups. Okay. So when it says that one has to prove that it's a trivial homomorphism between fundamental groups, it means that the latter fundamental group is it consists of the identity element only. Okay, and that makes the homomorphism trivial. Okay, all right. So let's prove that 1 implies 2. That's the first step. We're going to prove first that 1 implies 2. Here goes the proof. Let H from S1 cross I to the topological space X be a homotopy between this continuous map H and the constant map Well, it's given that H is null homotopic, which means that such a homotopy exists. So we are taking that homotopy, we're calling that homotopy H. Okay. So H is null homotopic is equivalent to the fact that H is homotopic to a constant map. Constant map means that we have a map that maps all of S1 to a single point of the given topological space X. Okay. All right. So these are given facts. We need, well, okay, all right. So at this point, So we postponed the proof here and developed some machineries related to quotient topology. Okay. We already know basics of quotient topology from the review notes on points in topology, but I want to give to some extent a broader definition of quotient topology, and for which we have this discussion. Okay. So we need. So remember where we left. Okay, we need to have some results on quotient topology. At this stage first. Okay. And to this end, we give a somewhat broader definition of quotient map. Along the line of what Moncrief did in page number 136, compared to it's broader compared to what was done in the points topology review notes. Topology review notes. Okay, so I need some space here, so let me erase everything. Okay, we're back to discussion on points topology. So here is the thing. So if you can recall what we did in the points topology review notes, you see that we considered this canonical projection map from the topological space to the quotient space. Okay. Well, we should not call it a quotient space first. We call it a quotient set, and then we equip it with certain topology, and then we call it a quotient space, right? This is what we did in the review notes. Okay, and this is done. This quotient is worked out with reference to some equivalence relation tilde, with reference to some equivalence relation tilde on the given topological space X. Okay, and then we say that a subset of this quotient set is going to be open if its pre-image under this canonical projection map is open in the given topological space X. And this way we get a topology on this quotient set, and with respect to this topology we call this quotient set a quotient space. Okay, so this was done there. But instead of doing it this way, we would now consider a surjective map P from a given topological space X to another topological space Y. So now, instead of having one topological space X, we have two distinct topological spaces, X and Y. Okay, and we want this map P to be surjective only. Nothing else is required. Okay, so let P be a surjective map from the topological space X to the topological space Y. Then the map P is said to be a quotient map provided a subset U of Y is open in Y if and only if inverse image of U under P is open in X. If this is the case, we say that P is a quotient map. Okay? Okay, good. It follows from the definition above from the definition above that if P is a surjective continuous map that is either open or closed, then P is a quotient map. Okay. So what you need to do is that you first have to assume that this map P between these two topological spaces is surjective, continuous, and say first take it to be open. Okay. So you take this surjective continuous map P between these two topological spaces X and Y to be open, and then use this definition and immediately see that this map P is a quotient map. Similarly, using the definition of continuity, you can also check that if this map P between the topological spaces X and Y is surjective, continuous, and closed, then this map P is also a quotient map. Okay, you need to verify this. Okay, so the third point is that, however, there are quotient maps that are neither open nor closed. Please refer to exercise 3, page 145 of the Moncrief's book. Okay. It is instructed that you work out this exercise. Okay. Okay, good. Now we give the definition of quotient topology in this new flavor. Definition, quotient topology. Let X be a topological space. Okay. And A is simply a set if P from X to A is a surjective map So we want P from the topological space X to the given set A to be surjective. Okay. Then there exists exactly one topology on exactly one topology which we call tau on this set A, relative to which P is a quotient map. We know the definition of quotient map. Okay. So there is no more than one topology on A with respect to which P will be a quotient map. Okay. There is exactly one topology and we call that topology quotient topology. It is called the quotient topology induced by P. Good. So this was the definition of quotient topology. Now we define quotient space. Quotient space. This is something that we already encountered in the point set topology review notes, right? Let X be a topological space and let X star be a partition of X into disjoint subsets. Okay. So when I say a partition, it means that the union of all these disjoint subsets should give X. No. The union of all these disjoint subsets should be equal to X. In spite of that, I write it here, whose union is X. So recall from the point set topology review notes that we denoted X star with X with this quotient set X modded out by the equivalence relation in the review note. In the review notes. This is good. Now let pi from X to X star, which is the partition of X into disjoint subsets. Okay, so let pi be the surjective map. Surjective map, so which is nothing but the canonical projection map. Okay, that carries, so this map pi carries each point of X to the element of X star containing that point, and an element of X star is nothing but a subset of X. Okay, remember that the elements of X star are disjoint subsets of X. Okay, so X, so if we pick up a point from X, it is contained in only one element of X star. Okay, since the elements of X stars are all disjoint with each other, it has to be contained in exactly one element of X star. By an element of X star, we mean a subset of X. Okay, so each point of X to the element of X star, which is of course a subset of X. Okay, so it refers to this surjective map that carries each point of X to the element of X star containing that point, containing it. Okay, this is what pi is achieving. So now we invoke the definition of quotient topology. We see that pi is a surjective map. In the quotient topology, induced by this surjective map, which is the canonical projection map, pi, the space X star, which is the partition of X, right, is called a quotient space of X. Quotient space of X. So in the quotient topology induced by pi, the space X star is called a quotient space of X. Good. Okay, so in order to relate it with what we did in the point set topology review notes, one often says that there is an equivalence relation tilde defined on X by means of which the elements of X star so we know that the elements of X star are disjoint subsets of X whose union is X, okay, by means of which the elements of X star are called equivalence classes. So that is precisely the reason we denoted the quotient space with X modded out by the equivalence relation. This is so instead of using X star, we use this notation for the quotient space, so that this equivalence relation becomes manifest in this notation. Okay. Now, this broader definition of quotient map P is a surjective map between the given topological spaces X and Y, and this is not necessarily the canonical projection map pi from that one has from X to the quotient space. Okay. So in the review notes, we gave the definition of quotient topology with reference to this canonical projection map. But the definition that we have just given for this, the quotient map does not need to be necessarily this canonical projection map. It can be anything, any surjective map P between two topological spaces X and Y satisfying certain properties, certain topological properties, okay, that we already provided in the definition. Okay. Well, but this is the thing. But essentially, it turns out that if P is a quotient map between these two topological spaces, then Y is homeomorphic, okay, homeomorphic to the quotient space X modded out by this equivalence relation. Okay, this is true. This is given in one of the theorems in Moncrieff that we'll not study here, but this is true. So if P is, according to this broader definition, if P is a quotient map between these two topological spaces X and Y, then this latter topological space Y is homeomorphic to the quotient space X modded out by the equivalence relation. Okay. Without procrastinating anymore, let me state some very important results that we'll need to prove lemma 2. Okay, so that was the whole purpose. We need to prove lemma 2. Okay, so there is an important result based on this broader definition of quotient topology. Let me state the result without proving it. Theorem 2. Let P from X to Y be a quotient map with reference to the definition we just provided. Let Z be a topological space, and let G from X to Z be a map that is constant on each set inverse image of the singleton set Y under P for all Y in the topological space big Y. Okay? So we want G to be constant on each such set. Okay? It may be a singleton, so there is no, it's trivial then that G is constant on such a singleton set. But if it's not a singleton, then we demand that G is constant, G is constant on this set, meaning that for any at any point on the set we get the same value for G. Okay, alright. Then if this is the case, then G induces a map F from Y to Z such that F composed with P is equal to G. So let me draw a picture, a commutative diagram at this moment. So we were given a quotient map, first of all, from X to Y, which we denote by P. And then there is a topological space Z, and we have a map G from X to Z that is constant on each such set, okay, here. Alright, and if this is the case, then G induces a map F from the topological space Y to the topological space Z such that this diagram commutes, meaning that this holds. So this is the first thing. Then this is the second thing. The induced map F is continuous if and only if G is continuous, if and only if G is continuous. Okay, the third thing is that F is a quotient map. This guy F, this induced map F, is a quotient map if and only if this guy G is a quotient map. It is a very important result that we are going to use on several occasions in the rest of the lectures. Okay. So the proof is omitted. The interested readers can refer to the book by Moncrief for the proof. So so it essentially tells us that the property of the induced map F actually depends on the property of the given map G between the topological spaces X and Z. Okay, so now let's get back to the proof of lemma 2. So let me erase everything. We are going back to the proof of lemma 2. Back to the proof of lemma 2. Okay, so we already, so let me freshen up your memory a bit. We already denoted by H, which is a map from S1 cross I to the given topological space X, homotopy between the given map H. H was a map from S1 to X, right? It's a given map from S1 to X, which is also given to be continuous. Okay, and we also know that this continuous map H is homotopic via H to a constant map on X. Okay, H and big H is the homotopy between H and a constant map. So we want the following diagram to be commutative. We want the following diagram to commute. So here is the diagram. S1 cross I is a product space, and from which we have a map called pi to the unit ball B2. And from S1 cross I to X is the map which is the homotopy between the two maps H and the constant map. And from B2 to X is a map K. Okay, and we want this diagram to commute. So this is a figure. This is our figure 1 induced map. Induced map. The name of the figure is induced map K from B2 to X. Okay. So S1, so where pi from S1 cross I to B2 given by pi of x comma t to be equal to 1 minus t times x, being this map. Okay, being surjective, continuous, projection map is always continuous, right? And closed. So you have to verify that these things are true. That pi defined this way is surjective, continuous, and closed, and hence it's a quotient map. We have seen it earlier that if a map is surjective, continuous, and either open or closed, then it's a quotient map, right? So this guy, being surjective, continuous, and closed, is a quotient map. Okay, right. So the given data fit in theorem 2. We have these three topological spaces, right? and we have this map to be a quotient map, right? So we can say that this induced map K will be continuous if and only if H is continuous. And we know that H is the homotopy between the continuous map H and a constant map on X, which means that H is continuous, and which tells us that this map K is also continuous. Okay, so about this map, so let me give you a picture for understanding this map a little more clearly. Okay, in fact, we have a homeomorphism of S1 cross I quotiented out by the following equivalence relation. So it is nothing but a cylinder, right? So we are collapsing one end of the cylinder. That's what we are doing here, okay? X comma 1 is identified with X prime comma 1, okay? So at the end 1, we are going to collapsing the circle to a point and making it a cone first, and then we are smashing the cone to make it a two disk. Okay, so this guy is homeomorphic to the two disk. So let me give you a picture for this. So roughly this is what's going on. Let me draw the cylinder first. This is S1 cross I. Okay. This is the picture for S1 cross I. So let me draw 3 pairs of distinct lines. So this is one pair. So now this is another pair, and this is another pair. Okay, so this is the cylinder, and now we are trying to shrink this face of the cylinder. Okay, so let me draw a picture for this situation. We are shrinking the top face of the cylinder this way, so that the position of those vertical lines is now like this. Like this. Okay. Finally, we are collapsing this circle into a point to make it a right circular cone. And the position of those vertical lines are now like this. Right? Okay. Now we are smashing the tip of the cone to the center of this ball to get a unit ball. Something like this. which is B2. Okay, so this picture intuitively gives you an idea how this homeomorphism works. Okay, good. So let me give a title for this figure, which is figure 2. The map S1 cross I is so this is the the projection, right? This is the canonical projection of S1 cross I to the quotient space under the identification of the points on this circle. So x comma 1 is identified with x prime comma 1, and then you have this quotient space, right? And this guy is homeomorphic to the unit ball. Okay, so this is more generally what we have said earlier, that whenever we have a quotient map between two topological spaces, it means that the latter space is homeomorphic to the quotient space X modded out by the equivalence relation. So this is what's happening here. So because we are dealing with this quotient map, right? This was our quotient map, which we denoted by pi. Okay, and this guy is homeomorphic to the quotient space S1 cross I, modded out by this equivalence relation. X comma 1 is identified with x prime comma 1. Okay, good. All right. So now, recall that H from S1 cross I to X is a homotopy between the continuous map H and the constant map. Okay. Right? And what was pi? Pi was a map from S1 cross I to the unit ball, right? Given by pi x comma t is equal to 1 minus t times x. So this was the definition of this quotient map. Okay. Now observe that the inverse image of the point 0, 0 under pi, okay, is all of S1 cross the singleton 1, right? So no matter what you choose here, x from S1, as long as you take t to be 1, you will always get a 0 on the right hand side, which means that the inverse image of the point 0, 0 in V2, the unit ball under pi, is going to be this set. Okay, so this is one important thing. And the inverse image of B, the singleton B, is a singleton if B is not equal to 0, 0. For any other point B, it is going to be a singleton set. Okay. So why are we talking all this? Because let me draw that commutative diagram again, which I did a while ago. There was a map from S1 cross I to B2. That's our quotient map, right? Pi. And we have seen that there is a homotopy H from S, which is a map from S1 cross I to the topological space X. And we are interested in this induced map K from B to X. Okay. We want H, so we want to embed this diagram into the framework of theorem 2. So we want H to be constant on each of this set. Inverse image of P. Okay, we want H to be constant on this set for all B in the 2 disk. This is what we want to do so that we can apply theorem 2. Okay, which is actually true. Hence, so H is this. H is trivially constant on the inverse image of B if B is not equal to the point 0, 0. Why? Because it's just a singleton. So H is trivially constant on a singleton, right? And we have also seen that H is constant on the set inverse image of 0, 0, which is S1 cross the singleton 1. Why? Since H of x, 1 is E sub x0 of x, right? For some, this is the constant map, okay? And H was the homotopy between H, small h, and a constant. We're taking that constant map to be E sub x0 for some x0 in the topological space X, and the constant map E sub x0 from S1 to X. Okay, and this guy is defined by, of course, we know that everything is mapped to that point x0. E sub x0 at x is going to be equal to simply x0. This is how we define that constant map, and H at x comma 1 is just that constant map evaluated at x. Okay, so that h is indeed a constant here. So we are good to apply theorem 2, right? So from this figure we see that this continuous map H induces a map K from B2 to X such that this diagram commutes. In other words, K composed with pi is equal to H. This holds by theorem 2. In addition, since H is continuous, K is also continuous. K is continuous. Okay, so these are the results we obtained from theorem 2. Okay, good. I need some space. So K from B2 to X is continuous, which we have seen from by applying theorem 2. Also, since K composed with pi, we have seen that K composed with pi is equal to H. So K composed with pi evaluated at x comma 0 is K composed with pi is H, right? H of x comma 0, since H is a homotopy between small h and the constant map E sub x 0, right? H of x comma 0 is nothing but h small h of x, right? And it holds for all x in the circle, right? So what does it mean? It means that K restricted to the circle is nothing but this map H. Okay. Right? Right. So K restricted to this circle, the unit circle, is going to be equal to small h, right? Hence, h extends to a continuous map K from B2 to X, right? K composed with pi evaluated at x comma 0 is actually nothing but K restricted on this part, right? Since I'm just taking a slice from the cylinder, that means that I'm restricting my attention to the entire circle, not on this part. And that gives me, this map H this way. Okay, so good. So this way we prove that 1 implies 2. We get this continuous extension, which is this continuous map K from the two disks to the given topological space X. Okay, so now it's time to prove that 2 implies 3. Okay, so let me finish the proof of lemma 2. I want to do it, although this segment is getting longer, but I want to do it. So let's prove that 2 implies 3. So what was the statement 2? Recall that the statement 2 was that H extends, so the given map H, the given continuous map from S1 to X extends to a continuous map K from the two disk to the topological space X. Okay, this holds. Now we have to prove that the induced homomorphism H star is a trivial homomorphism of fundamental groups. Okay, let's do it. If J is the standard inclusion of the unit circle into the unit ball, then H is equal to K composed with J, right? So let me draw this diagram. S1 from S1 to B2 is the inclusion map J, and from B2 to X is the continuous map K, which is the extension of this map H, right? And then H is this map, right, which is the composition of these two maps K composed with J. Hence, H star is going to be equal to K composed with J star, and from the second lecture we know that this is K star composed with J star, right? Now since J star is the induced homomorphism between the respective fundamental groups, the fundamental group from the fundamental group of the circle, from the unit circle with reference to the base distinguished point B0 to the fundamental group of the unit ball with reference to the same point B0 is trivial. It's given that these J star this J star is trivial, meaning that So we have J star to be trivial, right? It follows so we have this fundamental group. Okay, so J is the inclusion map, right? And by lemma 1, it's so I didn't write it in the note that J star has to be trivial by lemma 1, since no, not by lemma 1. So why is J star trivial? Okay, J star is trivial because there is only one element here. Okay, we just have the identity element here because it's trivial. The fundamental group of the two disk or the unit ball is consists of only the identity element. Okay, the constant map. That meaning that the constant loop, that's the only element that is presented in this fundamental group. And so since we have this map J star from the fundamental group of circle to this fundamental group of the two disk, so all the elements here, group elements, are going to be mapped to that single element, here. That is the reason this induced homomorphism J star is going to be trivial. So that's what I'm writing. This is trivial, meaning that all the group elements of pi 1 S1 comma B0 are mapped to the identity element of the one element group pi 1 B2 comma B0. Okay, so from this relation we see that since J star is trivial, H star has to be trivial as well. H star is also trivial. What does it mean? So it means that the image of the map so H star is this map, right? So H was this map from S1 to X, right? This continuous map. So H star is from S1 comma B0 to pi 1 X comma X0. This is the induced homomorphism. And this is we have seen that this is trivial, right? H star is trivial. and that means that the image of H star is the identity element of the group pi 1 x comma x0. Okay. Alright, so this way we prove that H star is trivial. This is what we needed to prove, right? And that establishes that 2 implies 3. Okay, now we have to show that 3 implies 1. Okay, let's do it. We need to prove that 3 implies 1. So at this stage we will assume that H star is trivial, and then we have to show that H is null homotopic. Okay, so let P from R to S1 be the standard covering map of circle. Be the standard covering map given by P of x is equal to cosine 2 pi x sine 2 pi x. Alright? Okay, it's gonna be a long one. Okay, so this is the standard covering map. Also let P0 is a restriction of this covering map to the unit interval. Okay, so P0 from I to S1 be the restriction of this covering map P to I. That is, P restricted to the unit interval is nothing but P0. Okay, so it's evident that this class generates the fundamental group. Okay, this generates this fundamental group pi 1 of the unit circle with reference to this base point P0. So the base point is 1, 0. Okay. In fact, the elements of this guy can be written down as, dot P0 to the minus 3. This is one class. Then P0 to minus 2. Then one has P0 to the minus 1. Okay. So one has this constant map, so I'm not writing it here. Okay. So there is one constant map, right? So let's call it the 1, right? Then you have P0, then P0 square all the way up to infinity. Then you have P0 cube, all of them. Okay, so where you see that P0 to the n is this loop. P0 is the concatenation of these loops n times. The loop with itself n times. Okay, for n belonging to the set of positive integers. Okay. Similarly, you can write p0 to the minus n. This is the loop of p0 to the minus 1, p0 to the minus 1 n times again, p0 to the minus 1 n times for all n in the positive set of positive integers. Okay, so p0 and p0 to the minus 1 are the equivalence classes of loops of the unit circle based at b0, oriented counterclockwise and clockwise respectively. This is counterclockwise, and this is clockwise respectively. All right. So you take, it means that it wraps around the unit circle n times in the clockwise direction, and it means that this loop wraps around the unit circle, okay, starting from b0 counterclockwise n times. All right, good. So we just have seen that this fundamental group of the unit circle with reference to the base point b0 is generated by the loop what is the loop? P0, the class of the loop P0. So any loop can be written down as an integer power of this loop. Okay. Now, since H is this map from S1, B0 to X, X0, H is a continuous map between these two pointed topological spaces. H star, the induced homomorphism, is the homomorphism between the respective fundamental groups, right? So this is how this works. If I choose a loop from here that is going to map to H composed with P0, right? Under this induced homomorphism. Okay. So in other words, H star of this class is going to give you this class here in this fundamental group. So okay, so now since this is a based map between these pointed topological spaces, we must have H of B0 to be equal to X0. Okay, so we are given that. So we are proving 3 implies 1. Okay, so which means that we are given that H star is trivial, because H star is trivial, the loop F, which is equal to which we take H to be equal to H, this loop, okay, in the pointed topological space X, X0. F is a loop there. F H composed with P0 represents the identity element of this fundamental group, right? Because H star is trivial. So this is trivial. This map is trivial, meaning that all the elements from this group are mapped to the identity element here, and well, H star of P0 is going to be and the identity element here, okay? Therefore, this has to be the identity element or the constant loop. In other words, F is path homotopic to the constant loop at x0. Okay, this is what we said a while ago, that that's the only option since H star is trivial. Okay, therefore there is a path homotopy F. Therefore, there is a path homotopy which we denote by F in X between F and the constant loop at x0. Okay, so this is the path homotopy between F and the constant loop at x0. So let me get rid of this part. The map, so now focus on this map P0 times the identity map, which is a map from, since P0 is a loop on the unit circle, it's a map from I to S1, right? I to S1. And identity map is a map from I to itself. So P0 times the identity map is going to be a map from this product space I cross I to this product space S1 cross I. And that's given by P0 times ID acting on S comma T. So P0 cross ID evaluated at S comma T is going to be equal to P0 of S, which is a point in which is a point on the unit circle, right? And T is mapped to its node. So we get T. So under the identity map, we get T back, right? So the image of T under the identity map is T. So that's the pair that we have at the end. So this, you need to check that this is surjective, continuous, and closed. So this is something that you need to check. Okay, and hence it's a quotient map. Okay, so let me erase this part. So now see that P0 times ID, the identity map, evaluated at 0, comma t, right? So, which means that P0 at 0, right? P0 at 0, comma t. And P0 at 0 is the point B0 at the unit circle, on the unit circle, right? The distinguished point where the loop starts, right? And ends. And since it ends at the same point B0, since it's a loop, P0 cross ID evaluated at 1, comma t is also B0, comma t. And they hold for all t in the unit interval. Now, P0 times ID is otherwise, that is on 0, comma 1 cross I injective. Only at the, see that P0 cross ID is a map from I cross I to S1 cross I, okay? So the domain is I cross I. So, so we have seen the behavior of this this map on the two extremes of this, at the two extremes of this I, right? At the two endpoints, at 0 and at 1. Otherwise, it's going to be injective. In the interior of this unit interval, closed unit interval, it's going to be, this map is going to be injective. Okay? Now, F being a path homotopy between the loop F and the constant loop E sub x0 and the constant loop E sub x0 in X is a map from I cross I to X with F at S comma 0 is equal to F of S, and F of S comma 1 is going to be equal to E sub x0 at S, which, since it's a constant map, is going to be equal to x0 for all S in the unit interval I, right? Since F is a path homotopy between these two maps. Okay, and they both start, well, F0 comma T well, what is F of 0? F of 0 is going to be, what is F? F is H composed with P0, right? H composed with P0 at 0 is H of P0 at 0 is H of B0, and we know that H of B0 is equal to x0, right? And f of 1 is going to be equal to h composed with p0 at 1, right? And we know that again p0 of 1 is b0, since b0 is a loop in S1 starting and ending at b0. H of b0 is x0, so that the initial and final point of the loop f is x0. This is going to be x0, which is the same as f of 1 comma t. Both the loops f and e sub x0, they begin and end at x0, right? So this is what we have for all t in the unit interval. Okay. Right, let me erase this part. Hence, the path homotopy f from I cross I to x maps 0 cross I, this 0 for all t and I. So this maps 0 cross I, 1 cross I, and this is I cross 1 for all s. And I cross 1, everything to the single point x0 in the topological space X. Okay, at this point we need a figure, a commutative diagram. Again, we are going to embed everything in the framework of theorem 2. So we have this topological space. I'm running out of charge, so let me connect my charger to my laptop. Alright, so now there is this topological space I cross I, from which we have this map P0 cross ID to the topological space S1 cross I, and there is this homotopy, path homotopy, big F, from which is a map from I cross I to X, and it is going to induce a map H. Okay, and we want this diagram to commute. Let's see if we can make it commute using theorem 3. This is our figure 3. Okay, so each point. So in order to enable us to apply theorem 3, we need to ensure that f is constant on each of these sets. Each of these sets. Each of this set. Okay. So we need to show that f is constant in each of these sets. So each point of type B0, t in this topological space S1 cross I has two pre-images. under P0 cross ID, that is 0 comma t and 1 comma t. Because we have seen earlier that let me rewrite it. P0 cross ID at 0 comma t was found to be B0 comma t, and P0 cross ID at 1 comma t is equal to B0 comma t for all t and the unit interval I. We have seen this earlier, right? So that explains why each point of type B0 comma t has two pre-images under P0 cross ID, 0 comma t and 1 comma t. Okay? At all other points, x comma t, that is x in S1 set minus B0, the base point, and t is in I, the inverse image of x comma t under P0 cross ID is a singleton, meaning that everywhere else it's injective. Okay. Since f of 0 comma t is equal to f of 1 comma t equal to x sub 0, okay, because both the loop f and e sub x0 begin and end at x0. Okay, therefore we have seen that f of 0 comma t and f of 1 comma t is x0. One sees that f is constant f is constant on the inverse image of x comma t under P0 cross ID for all x comma t in S1 cross I. So this is what we have checked. Now we can apply theorem 2. We get, we have the usefulness of theorem 2 now. Okay, so let me erase everything. Therefore, using theorem 2, one immediately finds that so let me draw the commutative diagram again. We have I cross I, then there is this map which is of course a quotient map, right? Did we prove that it's a quotient map? Yes, we did. I asked you to check that it's surjective, continuous, and closed, and hence it's a quotient map. So P0 cross ID is a quotient map from I cross I to S1 cross I, right? And we have also shown that this map H is constant on all the pre-images under this map. Okay, this. Okay, sorry. So this is not H. This is F, and we denote this guy as H. One immediately finds that the homotopy, which is a continuous map, of course, the homotopy F induces a continuous map H from S1 cross I to X, with respect to which this is our figure 3, with respect to which figure 3 commutes. Okay, which means that H composed with this product map P0 cross ID is equal to this homotopy, path homotopy at big F. Okay, so now it means that therefore H composed with P0 cross ID at S, 0 is equal to H of P0 cross ID at S, 0, and this is nothing by the definition of this product map. It's going to be P0 of S, 0, okay, and and that has to be equal to F, right, which is F of S, 0, and we know that F of S, 0, big F of, since big F is a path homotopy between small f and the constant map E sub x0, it is supposed to be equal to F of S, right? And by the definition of the loop F is equal to H composed with P0, right? This is nothing but H of P0 of S. Okay, that is H of, so just writing P0 of S is a point on the unit circle. Okay, and any point can be obtained this way because the map P0 is surjective, right? So H of T, 0 is equal to small h of t for all t in S1. This is one important relation. Okay, so then we have H composed with P0 times ID evaluated at S, 1 is equal to H of P0 cross ID at S, 1, okay, which according to the definition of this product map is going to be equal to P0 of S, ID of 1 is just 1, right? And from the commutative video of this diagram, it's going to be F of S, 1, and F of S, 1 is the constant map E sub x0 at S, right? So far so good. Let me erase this part. Now I'm going to define a constant map E sub x0 tilde from S1 to X with E sub x0 tilde of S is equal to x0 for any S in this unit circle. Okay, so that one has E sub x0 tilde composed with p0 is going to be equal to E x0. Okay, this is how I'm going to define E tilde of x0. Well, P0 is a map from I to S1. So this is how we are going to define E tilde of x0. Okay, and then using that constant map on X, one writes EX E tilde sub x0 of P0 of S, right? So that makes me write H of t comma 1 is equal to E tilde sub x0 of t for all t in S1. Okay, so we just have seen that h t comma 0 is equal to small h of t for all t in S1, and we have also seen that h t comma 1 is this. So hence the continuous map, so the continuity of this map follows from the continuity of the path homotopy big F by the use of theorem 2. So hence the continuous map H from S1 cross I to big X is indeed a homotopy between the map H from S1 to X and the constant map E sub x0 tilde from S1 to X. Okay, so that proves that H is null homotopic. So this way we prove that 3 implies 1. Okay, so that proves lemma 2. Okay, so we're done with the proof of lemma 2. In the next segment we'll start with a corollary to lemma 2. Thank you for attending the first segment of the 5th lecture.